Okay, we can start our second example. Okay, so in the last lesson we analyzed our kinematics of the mechanism using the graphical method. So this graphical method is valid only for one given position of the mechanism. If you want to compute the velocities and accelerations of points for the entire let's say the period of operation of the mechanism, we have to compute it for some for a few positions of the mechanism in space, and then for example when we have the values we can interpolate the values using some interpolation scheme. But we don't have any functional relation between the input motion uh, and the output motion. So we cannot tell what's going on to the mechanism with the mechanism in every moment of time. But in case of the kinematic analysis by analytic method, it is possible. Our goal is to find a functional relation which governs the output as a function of input. And here I'm going to present how to model the mechanism using the closed vector polygon and how to solve for unknown variables which come from this analysis. Of course, also after showing you how to perform this kinematic analysis, I wanted also to show you that all the kinematic quantities which we have to think about using the graphical methods appear almost automatically after we differentiate our equations in these methods. So, for example, we don't need to worry about the Coriolis, is it present or not in our mechanism, because if we draw this vector polygon correctly and we correctly differentiate the equations, the Coriolis acceleration will pop out almost automatically. So we'll see at the end of this presentation. So first of all, this is the case which some people had trouble with, because most of the examples have this rotating rod as an input motion. There are no examples in book or in the lecture materials given to you by lecturers that have input motion as rectilinear motion, as you can see. But of course this kind of motion is very let's say common in the mechanism. This is just a let's say hydraulic or pneumatic actuator, which or maybe the electrical linear drive and so on. So we also have to analyze the mechanism in which the input motion is this rectilinear translational motion. You have to remember that even if on your drawing there is no vector, no displacement drawn for this input motion, we cannot forget that there is this, the motion is present. So as I showed on this example, we have to choose one fixed point. Let's say let's make it is called 0, or I don't know, any name you can, and we have to start drawing our vector polygon from this point. So here, as you can see, there is a point which is at the distance s1 from the point a1, and this point represents the motion of an input link. And we cannot forget that this motion must be present because this is our driving motion in case of this mechanism. So as you can see, this is one of the proposition, I think, of the vector polygon, it's let's say the simplest one. So we start with a vector L1 and we proceed with the other vectors, drawing the outline of the mechanism. And because the vector has to be closed, then the last vector L0 must return to our fixed starting point. And we have this vector polygon L1, L2, L3, L0, which represents our mechanism. As you can see, I haven't drawn the vector to the point D, because when we compute the omega free, let's say, and the epsilon free, the rotational motion, the rotational velocity and the acceleration of a link free, then it will be it is very easy to compute the velocity and acceleration of a point D, because this is just a rotation with a given angular velocity and angular acceleration. Therefore, it is not necessary to draw the vector also to this point. Okay, so our vector polygon, and we know that irrespective of what is going on with the mechanism, irrespective of its positions and orientation of its elements, the vector sum of this vector polygon must be equal to 0, because this polygon is always closed. It starts from a fixed point and it ends also with this fixed point, the same point. So we know that L1 plus L2 plus L3 plus L0 is equal to 0. And our goal is to solve this vector equation to find the unknowns. So let's first analyze these vectors and see what is known, what is unknown in our example. But before that, I wanted to also tell you about this convention. As you can see at the bottom of the page, there is a frame of reference, and the convention is that all of the angles of the vectors have to be the angles between the positive x-axis and the vector. So these vectors can be, acute, obtuse, and so on, but it also is a vector which these angles can be acute, obtuse, and so on, but always these these angles of the vectors are with respect to the x-axis, positive x-axis. When you use this assumption, then we don't need to worry about the signs between cosine and sines, because the signs will be given to us by the sign of the cosine, because you know that there is a change of the sign of the cosine and sine depending on the quartet of this frame of reference. So by using this convention, the signs are given to us by the trigonometric functions. We don't need to think about that, and we can just draw the sum of the projections. So let's see what is known, what is unknown. So first of all, L1. This vector represents the motion of the driving link, so the direction is fixed, and also we know the magnitude of this vector as a function of time, because we assume that this is given to us. L1 is equal L1 as a function of time. L2 is a fixed vector, both in the magnitude as well as in the angle. L3 is the vector which changes the length, the magnitude, as well as its angle. So there are two variables in this vector. L3 is a function of time, L3 is a L3 of t, and phi3 is a phi3 of t is the angle, which also changes. And of course the last vector is the vector which is between two fixed points, so this one is fixed. So we can project these vectors on two axes. As you can see, this equation gives you the projection of the vector sum on x-axis and on the y-axis. For some cases when this is not confusing, I just dropped the cosines and sines and just draw the values of these projections. But for the other cases, I wrote the L3 of t and cosine and phi3 of t specifically as a function of time, because we cannot forget that these are the functions of time. Otherwise, we'll make a mistake in the differentiation of these equations. So as you can see, S1 of t equals L1 of t is known and given to us, but there are two unknowns: the L3 of t, the magnitude of this vector, and phi3 of t, which is the angle, which is also unknown. Okay, so first of all, we have to compute these equations. So we need to find the functional relations between these quantities and the input quantities, as well as all of the constants. As you can see, there are two unknowns and two equations, so in principle we have to solve this, and we can solve this. So this is solved using the method for solving trigonometric equations. I haven't shown this in this presentation because this is not in the scope of the mechanics. It is just a simple algebra. So for example, when I look at this equation, I can give you a hint that you need to shift the terms with cosine and sines to one side of the equations, and for example you can divide these equations to obtain the tangent of the phi3 of t is equal to some value, and of course you can square both sides of this equation, add these two equations together, and using for example this trigonometric identity, sine square plus cosine square is equal to 1, you can simplify and find the value for L3 of t. So it is just a mathematics, it is not in the scope of these presentations. If you don't want to do this analytically, you can solve it numerically. It is not so important. You need to obtain this L3 of t and phi3 of t as a functions of time. Now we can go to the second part. So we need to compute the velocities L3 of t which is equal to v3 of t, and phi3 of t dot, which is equal to omega 3 of t. So one way is to having the equation for L3 of t and phi3 of t is to just differentiate these equations, but it's not advised, because first of all there could be fractions and square roots and so on, and arctangents and something like this, and the differentiation can be very hard to do. So when you differentiate the let's say this equation instead of the solutions, then the differentiation is easy. It's just differentiating of cosines and sines, and remembering that you need to differentiate the product of functions and the functions inside other functions and so on, so you cannot make a mistake doing this, but in principle it is easier. So you differentiate two equations to obtain the new two equations for velocities. And in these equations, v1 of t is given to us. As you can see, there is a computed differentiated velocities, as you can see, and maybe I just analyze the first equation. S1 of t plus L3 of t times cosine phi3 of t minus L0 is equal to 0. I differentiate this, so I obtain v1 of t times And here be careful, because this is the product of two functions. So you need to, after differentiation, you need to obtain two terms. The first term is v3 of t times cosine phi3 of t minus, in the second term, L3 of t times omega 3 of t times sine phi3 of t. And don't forget that in this term there is a function inside the function, cosine phi3 of t, which is also a function. So after differentiation you need to use the chain rule. And of course L0 differentiated is equal to 0, because this is constant. So you obtain these interesting equations. You will do the same for the second equation. You obtain the system of equations, and look at this. The only unknowns is the velocity v3 of t and omega 3 of t, the angular velocity. But as you can see, these equations are very easy to solve, because now these equations are linear in these unknowns. So there is no cosines inside and so on, no trigonometric equations. This is just a linear equation which you can solve easily using, for example, Gaussian elimination, using maybe even the so-called determinant method, which is not advisable for a large system of equations, but 2 by 2 is enough. So it can be solved very easily. Okay, so let's go to the second thing. Okay, maybe first, also I told you before that when you differentiate these equations, these projections of the vectors, you should obtain the same terms which you analyze using the graphical method. So these are not exactly the same, because, for example, there are the projections, and you first to introduce numbers to see the same length and so on. So this is not exactly the same, but the terms in the differentiated equation correspond to the terms in the vector equation you used having the graphical method. So as you can see, when you analyze it, you look at this carefully, you see that v1 of t is the velocity corresponding to va. This is the input velocity. v3 of t times cosine phi3 of t is also a velocity, or a projection of velocity, corresponding to the vb to b3. Why? Because v3 of t is the velocity of a change of length of the vector L3, and this change of length corresponds to the relative motion of a slider with respect to the rod. Also, when we look at the last term, L3 of t times omega 3 of t times sine phi3 of t, this term corresponds to the velocity which comes from the rotation of a rod vb3. Why? Because we have omega, which is the angular velocity of a rod, times L3 of t, which is the distance between the point B and the center of rotation. So as you can see, solving this, we found all of the velocities which were present when we analyzed it graphically. Also, you'll see that it is even more helpful in the case of the accelerations. Okay, so now after this we take the equations for velocities which are given to us on the slide, and we differentiate them once again. In the slides I just differentiated the first equation. You just do the same for the second one, and you also obtain the new system of equation, which is linear in new unknowns, linear in epsilon 3 of t and a3 of t, and also can be solved using methods for solving linear system of equations, even the determinant method. Okay, but look at this equation. You have to differentiate three terms, and remember about two things. that you differentiate the multiplication, the product of two functions. So you have to do the rule for the product of differentiation of the product of functions, and you also differentiate the functions inside other functions, so you need to use the chain rule. When you remember and you don't make any mistake in differentiation, you should obtain the terms I have on my slide. We also try to analyze this again, look at the similarities between this and the graphical method, but first of all look at this, that after differentiation there are two identical terms, so we can simplify this equation. Just add these two terms together, you obtain the 2 before the term, and I think you see what is this 2v times omega term, but let's see how it looks in our case. So here this is the comparison between all of the terms used in the graphical method and the terms which we automatically obtained using the differentiation. So a1 of t is, of course, like in the previous example, the acceleration corresponding to AA, and this is the input acceleration. A3 of t times the cosine phi3 of t. This is the term which corresponds to AB3 B2 AB2 B3. As in the previous case with velocity, it was the relative velocity of a it is now the relative acceleration of a slider moving along a rod. So it must, and it corresponds to the change of the length of the vector L3. So it must correspond to the AB2B3. The next term I've written here, L3 of t times epsilon 3 of t times sine phi 3 of t. We have the epsilon 3, the angular acceleration, times the distance between the B and C, so it must correspond to the tangential acceleration of point B3. Similarly, L3 of t times omega 3 of t times cosine phi 3 of t corresponds to the normal part of this acceleration, because we have omega squared times the distance, which is the equation to computation the centripetal acceleration. And of course 2 times v3 of t times omega 3 of t times the sine phi 3 of t is corresponding to the Coriolis acceleration. We have 2, we have also the relative v3 of t velocity, and we have the velocity omega 3 of the rotating frame of reference. So as you can see, even if you don't, if you forgot about the acceleration, all of the terms of the acceleration in the graphical method, when you do the analytic method correctly, you should be able to identify if you make any mistakes in the graphical method, because after correct differentiation of the projection of these vectors, you should be able to see all of the components of the acceleration. They should appear automatically after differentiation. Okay, I think we have to finish this presentation, and the next presentation topic will be analysis of the forces acting on the mechanism.